So today we're going to talk a little bit, I'm going to connect some stuff that we've done with, I'm recording. Yes, I think it's recording. I hope it's recording. I think it's recording. That's why I'm talking like this. No. So we're going to connect some stuff that we've done in Chapter 1, and now we're starting officially Chapter 2. Chapter 1 was all about limits. Chapter 2 is all about derivatives. Okay, next year in calculus, Mrs. Poole will start with Chapter 2, so she'll kind of redo all this stuff for you guys. If you're in AB next year, you'll start with Chapter 1, right? So you'll get a whole review of the whole thing. But Chapter 2 is super important. It gives you the basis of what is a derivative, what does it mean to take derivatives. It's called differentiate, okay? So it's kind of cool, it's kind of exciting. You're finally going to learn what this crazy thing called a derivative is. So we're going to start, though, by talking about the tangent line with the slope. And you guys already did this, finding the slope of your tangent line. So you know this equation. Now, I need another marker. Hold on. I had actually given you guys sort of a slightly different equation, right? So we had said that the slope of the tangent line before was the limit as x approaches a of f of x minus f of a over x minus a. We're going to change that a little bit and use this new definition of the slope of a tangent line. Okay, so it's very similar. It's still change in y over change in x. It's still a slope. But using now this notation here, it's actually very similar to the other one that we had done. I think we had said as x approaches h of f of x plus h minus f of x over h. So this was one we had done before as well. Okay, but instead of those h's now, we're going to change them to delta x's. And it makes more sense to change that to delta x because what that's talking about is the change in x. And we want that change in x to approach 0. We want it to be a very, 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 very small change in x. That's what the limit that we're talking about, right? So we want that change in x to be very small in order to simulate here the limit and the slope of the tangent line. This definition, you want to memorize it. You want to know this one. So it's the limit as delta x approaches 0 of f of c plus delta x minus f of c over delta x. And again, they just changed it to c's instead of x's. Not a big deal, but you do want to memorize this guy. Yes, sir.
Are we being quizzed on it?
There will be a quiz. I'll talk to you guys more about the quiz once everyone gets here. I want to say it's not till next Monday. No, Monday there's no school. Tuesday, maybe? Tuesday, Wednesday, something like that.
Is it going to be like the same format as the content?
No, this one will be more involved. So you'll actually have to do a lot more problems and stuff. So yeah, and we'll talk more about it next week. All right, so the slope of the tangent line is also called the slope of the graph. Sometimes you'll hear me say that. Instead of just saying the slope of the tangent line, we're actually finding the slope of that graph of f at that point C. All right, so let's go through and just do a linear one using this new formula now. All right, so you can get used to it. Obviously, we know that the slope is going to be 2 here, right? It's a linear graph. 2x minus 3, the slope has to be 2. But let's actually go through the long way and figure this out. So we do the limit as delta x approaches 0. And now you have that c value, right? It was f of c plus delta x. So instead of c, you're going to actually plug in that first x coordinate, okay? So I plug in a 2 plus delta x minus f of 2 all over delta x. So now let's work this out. Well, my equation is 2 times x minus 3, so I'm going to plug in here. This will be the limit as delta x approaches 0 of f of 2 plus delta x. I'm taking 2 plus delta x, plugging it in for x. 2 plus delta x minus 3. And then I'm subtracting off f of 2. Well, what's f of 2? It's just 2 times 2 minus 3. All right? And that whole thing is over delta x. So now I'm taking the limit as delta x approaches 0. And I'm going to work this guy out. So I'll have 4 plus 2 delta x minus 3 minus 4 plus 3. Cancel, 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 cancel. All over delta x. Oh, look how nice. My delta x's even cancel out now. And so I have the limit as delta x approaches 0 of 2. Well, that's just equal to 2. Take a sec and make sure that makes sense. Again, we knew our answer was supposed to be 2. That was going to be the slope. It's linear. The slope is 2 anytime, right? Go ahead. Yeah. All right, so that first example is kind of like, really, why did we have to do that? We knew the slope would be 2. It's linear. Well, what happens now when we have a different graph? This next one's going to be a quadratic, okay? So for a quadratic, the slope is not going to be the same everywhere, right? Depending on where you are on that curve, your slope is going to change. It could be positive, it could be negative. So it really depends on what point you're at. So we're going to use the same thing. We're going to start by doing this generically with C's. Okay, I'm not going to plug in the 0 or the negative ones yet. We're just going to do it with the C's to start. And this is how you'll do a lot of these problems. You'll keep it with a C or with an X or with a variable. And then later you'll plug in the numbers. So let's do our equation here. This is the graph we're doing, x squared plus 1. So f of c plus delta x. And just make sure every time you are writing, the limit as delta x approaches 0. Okay. So f of c plus delta x, I'm taking that and plugging it in for x. So I'm going to have c plus delta x squared plus 1. Then I'm subtracting off f of c, which will just be c squared plus 1, all over delta x. You're just going to get used to this whole delta x notation. Delta x is just a variable, okay? Just bring it along. All right, let's work this out. So c plus delta x squared is just c squared plus 2c delta x plus delta x squared plus 1 minus c squared minus 1. I just FOILed this guy out. All over delta x. Cancel, 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 cancel. And then the delta x's all cancel out as well, right? And that's kind of our goal, is to get rid of that delta x on the bottom. And one of them's gone there. And so what am I left with here? I'm left with the limit as delta x approaches 0 of 2c plus delta x. Agreed? The 2c from here, and then there's a delta x there. Now I'm trying to find the limit as delta x approaches 0. So I take this delta x and I can do direct substitution, and I get 2c plus 0, or 2c. This formula that you get here at the end is very important. This is called the slope generator. I don't know if that's the official term, but I call it the slope generator. Why do I call it the slope generator? Because it will generate the slope for you at any point, c. Okay? So if I plug in a 1 for c, it'll figure out the slope at x equals 1. If I plug in a negative 10 for c, it'll find the slope at negative 10. If I plug in 252, it will find the slope at x equals 252. Does that make sense?
Yep.
So again, it's the slope generator. Okay, well they wanted us to find the slope at these 2 points. So just plug in your 0, plug in your negative 1 for c. So let's find the slope. So the slope at 0, 1 is just going to be plug in a 0, 2 times 0, answer is 0. And then they also wanted the slope at negative 1, 2. So I plug in a negative 1, and I get negative 2. The c is always the x value. So you're always plugging in the x value. Think about the graph for a second and see if this makes sense, you guys. The graph was x squared plus 1. It's a parabola. Okay. At the point 0, 1, it says that the slope is equal to 0. Does that make sense that the slope of the tangent line right here would be 0? Yeah, totally. It's got a horizontal line right there. So it's going to have a 0 slope. How about this one? At negative 1, 2, wherever that is. Does it make sense that that slope would be negative 2? Yeah, look at that slope right there. Looks pretty good. Okay, so you can always do a quick sketch of the graph, double check, does it make sense, the slopes that I got? And using that slope generator, you can get it anywhere you want. Okay, right now we're using the definition here. Okay, this definition is sort of the long way to find the slope generator. In the next section, we're going to learn a fast way to find the slope generator. Okay, which you'll be like, why do we have to do it the long way? You'll be very mad at me, but that's okay. You have to learn it the long way first. That's how it always goes. All right, questions? Okay, let's keep going. the definition of a tangent line to a curve does not cover the possibility of a vertical tangent line, right? The vertical tangent line, what kind of a slope does a vertical line have? Undefined. A vertical line, right? Undefined slope, right? It doesn't have a slope. So how would I find the slope of a vertical tangent line? Well, the issue with a vertical tangent line, that's when you're going to get that infinity or the negative infinity, right? So if you find the infinity or negative infinity, that's when we know we have a vertical tangent line. Okay. The moment you've all been waiting for. Definition of derivative. Dun, 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 dun. Here it is. You can actually go home today and tell your parents that you learned something awesome. Instead of just being like, nothing, we did nothing at school today. Like, we learned the definition of a derivative, Mom. I feel so smart. All right, so here it is. It's not as exciting as you've probably been hoping for. We're going to talk a little bit about notation as well. Okay, so the derivative of f of x, f at x, is given by. So this little notation is important. See this little, like, kind of like a tick mark there sort of thing? Yeah? That's called prime. Okay? We've seen that before when we did, like, transformations of things, and you would take a point and you transform it, and you'd have, like, a prime or b prime, right? So that little symbol, we say prime. So f prime just means the derivative. That's all that it means. You're going to get very used to this. You're going to see it a lot. So f prime just is the derivative. It's the most common notation for derivative. And all that it is literally the exact same equation that you guys just did. Except now we've gone back to x's instead of c's. Don't ask me why. The c's and the x's, and I could care less what you use in there, okay? As long as you get the right format here. So all that the derivative is, well, it's equal to this equation we just learned, but Ms. Rodriguez, you just told us that equation was the slope of the tangent line, right? So what does that mean? That means that the derivative
is the tangent.
You got it, is the slope of the tangent line. That is all that the derivative is. A derivative is a slope. That's it. And you guys know what a slope is. So you've actually known what derivative is all these years, and you didn't even realize it, right? Except now we're going to find the derivative of a quadratic and a cubic and a radical and all these other stuff, right? Whereas before you could only find the slope of a line. Now you're going to be able to find the slope of all these other types of graphs. So derivative is slope. Just memorize that, get it in your head. And now we know this is the formula for finding the slope. Okay? Provided the limit exists. And f prime is always a function if the limit exists. Okay? There's kind of a lot of stuff here, and this is good just to kind of get a background. The derivative of a function of f is also a function of x, The new function is the slope of the tangent line, right? That's what we just talked about, provided that it has a tangent line there. This next part is just about terminology, you guys. The process of finding the derivative, we don't say derivate. Some people think, why don't you derivate? That's not a word. I just made that up. That's not real. So what do we derive? You can say derive, but that doesn't go to derivative, okay? So what we say, like you could derive some formula or theory or something. So the word we use is differentiation. So you are going to differentiate to find the derivative. Does that make sense? So you'll start using this terminology. I'll say this stuff. We also are going to ask you about things if they are differentiable. If something is differentiable, it means the derivative exists, okay? And then we'll get into this open interval, closed interval stuff. Okay, notation for derivative. I just talked a little about this. With that little tick mark thing there, that little sort of apostrophe, that means f prime of x is the most common notation. There's a lot of other notation here, you guys, okay? So other times, instead of using f prime, you're going to see this, dy dx. That also just means derivative. Derivative of y with respect to x. That's exactly what we're talking about there. Y prime. Instead of f prime, you're going to see y prime. Other times you're going to say d of f of x over d of x. That's just the derivative of f of x with respect to x. And other times you're going to see a capital D with this little subscript x of y. So again, you're taking the derivative of y with respect to x. The nice thing is most of them have d's. So you see a d, it just means do derivative, okay? Or if you see a prime, it just means prime. Again, dy dx is read the derivative of y with respect to x. And again, it's just the same formula we just talked about, right? So it's the limit of the change in y over change in x. And again, this is the formula we were just talking about, and it just equals the derivative. So let's practice finding some derivatives. Turn the page. I got 3 examples to do, and then I am done. Do I have time? Is the big question. Okay, I'm going to stop for a second.